Welcome. I am your alchemist, Dr. Joyce Sherpa, and I'm here to teach you about chemical equilibrium this summer in Chemistry 223. The whole term builds off of this lecture, this week, this equilibrium idea. And so the first thing I have to tell you is it's all been a lie. All of it. Yes, I'm a conspiracy theorist, or I'm here to reveal it all. And it is not just me, those of you who've had me, but it's all of your chemistry teachers, unless you had an enlightened teacher. It has to do with these arrows. And we've always been showing arrows as if everything is one way, that there's only one direction you can go. But it turns out most chemical reactions, especially in our body, are a two-way street. They're reversible, and that's what chemical equilibrium is. And that's what we're going to talk about. All right. So, as I would have to wear a mask if I went to campus, we're going to be in my nice cozy little room here. And that allows me to dress up. And Janae had requested, why didn't we ever get to see that awesome purple one? And so I thought, well, why not for chemical equilibrium? So chemical equilibrium is just like it says, it's a balance point. And it's a balance, we gotta go through some terms to make sure. And by the way, since this is the first lecture, welcome, welcome, welcome all of you. I'm so excited that I will finally meet you. I'm videotaping this actually the day before I leave to go to New Jersey. And just in case when we come back, we don't make it for some reason, we have a delay, that you will still be able to access the first week until I get back. So some terminology is, we are always going to call what is on the left side the reactants. Now, I don't like the term left and right because in the classroom setting, I'm sometimes backwards to you, and I will tell you the truth, I get my lefts and rights mixed up. And I am aware there's a glare. We'll turn that off. Hopefully you can see this well enough. Probably not. You'll just deal with the glare. I highly recommend, I'm following along notes I'm going to be posting for you. And so you all have the capacity to print. You can go to a place to print if you're feeling safe, or some of you have notepads. You can take notes along. It is very helpful. And in the past, I required the students to always have the notes as I went along. It helps you to keep pace. You guys have a huge advantage since it's on video. You can stop me at any time that you get tired of me. All right, these on the right side, I always get my lefts and rights mixed up. People tell me to do the L, but you know what? You can make both hands look like an L, so that never worked for me. These are the products, the ones that are after the arrow. We call going in this direction from reactants to products the forward, and the other direction, going from products to reactants, we call the reverse. So I try to very much avoid using lefts and rights, and I ask you also, because most of us run into dyslexic issues. So you can use arrows, or reactants, products, forward, reverse are the correct terms to use. All right. So reactants, however the equation is given for that problem, these are the reactants, these are the products. And I mention that because this equation we will probably see again, and it may be written in the other direction. All right, a couple of things about equilibrium, a couple of important points is, besides these arrows like this, and you will sometimes see them written like that, it doesn't matter to me, they both mean equilibrium. And this is the whole term builds on this idea that actually most things are this balance point. So we talk about yin and yang. Well, it's actually that balance point in between. And that balance point doesn't mean that the reactants and products are equal. There is something that's equal. And you don't have to draw this graph, but it is something that you'll find in the books and in the explanations, that if we were looking at concentration, everybody can concentrate really deeply right now. Concentration, you will see me showing brackets, and that means the big M, which is molarity, and I'm hoping that you can see this well. If we are looking at this is time as the reaction proceeds, and we start with the reactants, right? I'll put an R. We can do some different colors, actually. We can do an R for the reactants, and the reactants will decrease, but they hit a point where they plateau. And that's what's happening with chemical equilibrium. So as these two are reacting and combining, what happens is the HI, as it's made, it starts breaking down. And you hit a point where the concentration doesn't change anymore. So this would be the HI, or product. Now notice they don't hit an equal point. They hit a point of balance. What is equal is the rates. That they hit a point, if we did this as rates and time, that they would hit a point where the reverse reaction is speeding up and the forward reaction is slowing down, and they hit a point where the rates are equal. And so that is what's actually equal in equilibrium. The other thing is this is very dynamic. So it's not that this reaction, we got that breaks down, and we have this, and it stops when it hits equal rates. No, they're always reacting and forming and breaking down. It's just they hit a point where we can't discern. There's no more changes in the concentration happening, but it is always a very dynamic, which is what life is, right? And again, we call equilibrium as reversible reaction. The other big point, and this is a huge one, is all the components must be present. So, and the other big point with this is it is a closed system. So I really like doing this with you guys there, because you can tell me, hey, if you can see my pens or not. So we're going to hope that you can. Or we'll just go to black. So closed system means we put a cork on it. If you have it open, what's going to happen is, well, the gases would have escaped. They probably wouldn't have even reacted to begin with, or as they make the HI, it's going to escape because they're gases. So we have to put a cork on it if we're thinking about doing it in a laboratory system. Or you and me, right? You put a cork in me, well, I got to keep breathing to talk to you. But we are kind of a closed system, but we're always putting stuff in, and we'll talk about that. My interest is in us and this planet. So, all right. But as a closed system, all the parts have to be there. So initially, when you mix the hydrogen and iodine, you're not at equilibrium because you haven't made any HI yet. Now, chemical reactions happen in femtoseconds, 10 to the negative 15th of a second. Yeah, there's 10 to the 15th power of them. That's a quadrillion, right? So a trillion is to the 12. So a quadrillion reactions are happening in a second. So it's pretty fast on our time frame. Like, wow, what just happened? More than a second passed. But all the pieces are present. If you took something away, you're not at equilibrium. And that's a huge principle called Le Chatelier's principle that we are going to get to later in the lecture. All right. Another big important piece about equilibrium is there's something called the equilibrium constant expression. And I'm going to erase this. And I use the squid hat because it erases this. Amazing. There you go. If you missed that, then you'll be asking the whole term. Why should you use a squid hat? So K. We write it as K, capital K. Okay? Got it? So K is called the equilibrium constant. We don't have to keep writing these words out. That's why it's nice to have your notes. It is correctly called the equilibrium constant expression. So sometimes, like in a homework question, it might say, write the equilibrium constant expression. And students are like, what? What does that mean? It just is, they're writing a fancy way of saying, write K. So shorthand, equilibrium constant, it is a capital K. If you remember kinetics, little k is what we used in kinetics. There is a way to relate them. That's really cool to relate them, but we're not going to spend too much time. We're not going to spend any time on that. These examples here, I'll do them over here, is, if I'm not in the way, we're going to write our K expression. Oh, so Actually, I'm going to do it for the top one up here. A reminder, periodic table. So I found my nice colorful one. Not that it really matters too much for this term, but you will need it eventually if we do stuff with molar masses. And so hopefully you have one or you can print one. And you should have one if you're here in 223. You must have used the periodic table at some point to make it this far. All right, let's go back to this equation and write our K expression. K is always products over reactants. It is a ratio. So that is why this terminology was really important. So the K for this expression, we show it as brackets because it is concentration. So HI, and then you raise it to a power. In this case, 2. That power is the coefficient. And then in the denominator, we will write our reactants. Now, the piece here is it's a ratio, so you're not adding, you're multiplying and dividing. So it's the hydrogen times the iodine. And again, those are brackets because they signify molarity. Concentration is what we're plugging in. You will see me get lazy, not lazy, efficient, and use parentheses. And I'm okay if you use parentheses, but just as somebody always asks me, shouldn't it be brackets? So that's our K expression. If we plug in molarity, it is technically called Kc with the little c. That c is usually left off. There is also something known as Kp, and we will run into it. I'm not sure that we run into it here in this very first lecture, but it is in these lecture notes. Kp stands for using ATMs, pressure. So instead of using molarity, which is all the other Ks, there is also a K sub A, which is when we work with the acids, so that would be molarity. There's a K little b for bases, which would be for this one down here, this example we'll get to. Actually, this one is an acid. There's a KSP, and so we look at all of this term. But when you see this as a Kp, it means rather than plugging in molarities, we're going to plug in ATMs. And so yes, we're going to get to review some gas laws. So some people ask me, oh, what do I do? Oh, yeah, so at some point, I guess I make a little video about the syllabus. Right, we're going to have a final exam that goes over everything. It's worth the same as your midterms. You'll be fine. You'll be fine. Don't worry. What you have to do here, you've already stopped. You stopped listening, but hopefully you're still listening. You need to trust me. Now, a quarter of this class has had me before. For 1, 2, or some of you for a whole year. And so you know, you're probably all sitting at home going, yeah, trust her. I have done this class for 25 years as an accelerated 5-week class, and there is review built in all throughout, all the study sets and things like that, or in lecture notes. So just kind of come along for the ride, keep pace, don't get behind. You can't get behind in 5 weeks. You also don't get burnt out, because usually it's the 5th week when you're like, oh, I'm so done with this, and it's like, oh, good, we are done with this. I'm like that. Maybe you guys aren't, but I am. All right. So Kp just means ATMs. Another thing, and this is actually really important, it's a ratio, and it's all about the ratio, products to reactants. Because it's a ratio, K cannot be a negative number. It's always greater than 0. So K must be greater than 0. It can be greater than or less than 1, and we'll talk about that, right? So K can be really big, like 1,000, or 1,000,000, or a quadrillion, or it could be really small, like 0.00001, but it's still a positive number. It's still more than 0. You can't have a negative ratio because you can't have a negative molarity in the world of matter that we're studying. And then the other thing has to do with states of matter. So you only include gas and aqueous. So these little g's are actually important. You don't include solids because of that statement I made earlier, where I said, as long as everything is there, you're at equilibrium. It doesn't matter how much solid you have. If you have any, or if you have a lot, you're at equilibrium. And so the solid doesn't have a concentration, right? Molarity is moles per liter. Solids don't have a pressure, so they don't have any influence. And liquid, really the only liquid we run into is water. And water is in so much excess. It also is a pure substance, and so molarity is solute and solvent, something in the water. So it technically doesn't have a molarity. All right, so we leave out solids and liquids. And so a recommendation I make is whenever you see, and when I teach this in my other class, they all do this. And what happens in here is some of you are so smart, you don't do it and you get careless. But whenever you see a solid or a liquid, just put a light line crossing them out. So that's why I'm using the red for that. So it means we don't include them in our statement. So let's go ahead and write our statement for these. And these were in the notes. So we leave the solid off. We do the reactants, the products. So magnesium, you want to show it as the ion. The +2 is in the brackets. And then the OH negative is squared. And then there's nothing on the bottom, but you can't have a 0, right? Because that makes it undefined. You can't put 0 into anything. So you can leave it how it is. Some students like to put a 1 there, and you can't. It just means it's over 1. It's whatever you have. Most of us just end up writing it like this. All right, if you ran into the situation where you had no products, we'll run into that at some point, you would have to put the 1 on top and then the reactants are on the denominator. But again, you're multiplying these, and that 2 is that coefficient here. And a question I do have for you is if any of you remember what the name of OH is. We run into it a lot because we spend 2 of our 5 weeks on acids and bases. It is hydroxide, ion, hydroxide. And so you're going to hear me use that word. The other big one is down here in the next one, which is the H3O positive. That is hydronium. And I will talk about acids and bases. That's our lecture in 2 days, typically Wednesday. So usually Monday and Tuesday. We usually spend 2 days on each topic, which would be a full week. All right, so that would be our K expression. And you don't have to put the little c. It's only if it's not KC that they put that little piece there. All right, and then for this one, we would write K equals. The only thing we're going to leave out is the liquid. I showed this one because you're going to see me, when I type, I sometimes have trouble. You have to show ions. You have to show charges plus and minus to denote that they're an ion. But if it is an ion, it is aqueous. So I often leave the aqueous off because the ion denotes that it's aqueous. So I just wanted to show you that. It's something you will see me do occasionally, and you can always ask. All right, that is acetate, and then times the hydronium. They both were just the 1 coefficient, so we don't show the power. So again, we're multiplying the products, and then the only reactant we're going to show is the acetic acid. So the whole thing goes in one bracket, CH3CO2H. And we leave off the H2O, because again, liquids, the H2O is always in so much excess. It's pretty much all there is that we ignore it. And solids, again, they don't change their concentration. All right, let me check my notes, see if there's something I missed. Oh, temperature. You're going to see temperature show up. And if you remember when you learned about density, temperature showed up way back when, beginning of 221, and density and equilibrium constants are temperature dependent. And so we will see that also when we get into Le Chatelet's principle in the second lecture series here. The other comment is units. K does have units, so technically it is different for every equation. Like here we have molarity times molarity divided by molarity. Remember doing this with rate constants? So you'd end up with the K would be molarity, whereas this one you'd have molarity times molarity squared, so it'd be molarity cubed. In my class, that's why our class is so special. Every class I've ever had, 25 years before you guys, also, we're going to leave the units off of K. So the only time we leave units off is K. When you're showing your work, you're going to have units, but when you solve for K, K is just going to be a number because K is the balance point. It tells us, do I have more products? Do I have more reactants? Where's your balance point? And that's where the temperature comment, it changes with temperature. So you have your balance point. You can't tell I'm standing on one leg here, stand on my head. We're live. I can do all these fun things. All right, let me see if there's anything else on my notes that I should tell you. Right, it describes a position of equilibrium. Do we have more products? Do we have more reactants? And we'll do practice with that. I've written these notes so we have those practice. It is dynamic, but that balance point stays how it is once the balance is found. So you know those rocks that you balance them and there's one specific sweet spot. I'm not very good at that game. All right, we're going to do the problem at the bottom of the page. So, all right then, erasing. You watch me erase. Here's that problem at the bottom of the page. If you didn't print the notes, you probably go, oh man, I should have printed the notes. Well, stop me because I'm videotaped. And go print the notes because it does help. Or you can be like, oh, I don't need notes. Oh, I liked how my other teacher did it. Well, good for you. You got stuck with me. So, when you do problem solving, first thing you want to do is write your K expression. Always write your K expression because this is algebra. Algebra's awesome. All right, so PCl3 and chlorine, everything's gas, so we're not crossing anything out. We're multiplying, and then the PCl5. Notice the subscripts are inside. There was no coefficients. And then the problem, so this is our algebraic equation. And now we just plug in. So the PCl5 down here is 0.860 ATMs. The K was given in the problem. I wrote over there. It's 0.497. And the PCl3 I think I gave you is 0.350 ATMs. And the piece I don't know is the chlorine. So it's just algebra. We know the other pieces. We rearrange. We solve for x. So we're going to have a lot of x's this term. We're going to have a lot of x's. Please always tell me what your x means. When you say x equals, say x equals my concentration of chlorine. Or more correctly for this one, you could also say x equals the pressure of the chlorine, because that's what it equals. So that's a P with the subscript Cl2. I apologize, I'm still new at this, doing online videos. It's really hard on me to put myself out there like this, but I'm doing it. So your loving kindness I would be very grateful for. K does not have a unit, but X always has a unit. In this case, since it was KP, it is going to be in ATMs. There is a note, a little disclaimer at the bottom there. I actually put in answers for all these problems. I did that this year, and I know my answers are right, but I may have done a typo, because that's what happens. My eyes and my hands aren't always perfectly coordinated. That's why I'm not a professional baseball player making billions of dollars to just sit home and do nothing, to make videos that everybody wants to watch. All right, we're going to do some calculations. You ready? Water, and let's go for it. Here we go, pop quiz. Why do I erase with a squid hat? Jason does this. Right. So we're gonna do some calculations. Usually this is this beautiful first day where I see all your smiles and we meet each other and greet each other, and all right. So you all meet me. So you only have one name to remember. So we're going to do some calculations, and I redid my notes. I rearranged them. So let's write out the equation first, because this will help me. Oh, I should grab black, sorry. See, this is good black. So our equation, we're back to this that I just erased. Hydrogen, iodine, 2HI. Again, however it's given in the problem. Sometimes I write it the other way. And what we're going to do is we're going to make ice charts. we do a lot with this term. It's summertime. I don't actually like ice. I went to school for Chinese medicine. That was my 3rd degree. And in Chinese medicine, your spleen, your digestion has to warm everything up. So they don't believe in using ice when they're cooking. And they also believe that everything should be cooked mildly. That probably has to do with the whole cholera and germ stuff, amongst other things, but it really has to do with an energetic thing. So the I stands for initial. In the problem, it will tell you if something is at equilibrium, that's what the E stands for, equilibrium. If you go back to the previous page, question, which said number 3, it said at equilibrium. The first 2 words will say at equilibrium. If you're at equilibrium, you don't have to do an ice chart. But if you look at this problem that we're doing, it doesn't say we're at equilibrium, it just says we mix some stuff. So it says we mix some hydrogen. So this is how we organize the information. So we have, all right. So some students like scientific notation and some of you don't. I am going to change this out of scientific notation because it's often easier for some students to see it. So it is 0.005 moles. Or you can say 5.00 times 10 to the -3. We would technically have our other 2 sig figs, and we'll talk about sig figs as we go through it. We should respect them. This chart needs to be molarity. Or if we're doing KP ATMs, we're not going to do that on this page, it looks like. So we need the volume. So we are going to have to divide by the 5 liters. So if we do that, this is actually 0.0, move our C down here, 0.001 molarity. This chart needs to be in molarity. All right, and then we mixed it with some iodine. So 0.01 moles over our 5 liters is what, 0.002 molarity. And that's it. We're at some temperature. Temperature doesn't matter in the calculations. It will matter for some questions later on. All right, and then we analyze it at equilibrium. And now you see it says at equilibrium, we find that we have the HI is 0.00187. And that has a capital M, so that is molarity, which is moles per liter. That is probably the most important unit you can have in chemistry, and we use it all the time this term. So I had one of my top students who is now a medical doctor he's doing his internship down in St. Louis, and it was like before the first midterm in this. He was my top student the whole year round. It was right before the midterm. He says, "Is there any questions before we start?" And he goes, "Yeah." And there were 60 students in the class that summer. And he said, "What does the capital M stand for?" The big M. He actually said it that way, like, when you're 5 and you say, "What's the big M mean?" And the whole class, dead silence. And everybody just looked at him and they looked at me, and I'm just looking at him going, "Really? How'd you make it this far?" And I was the only one who knew what his grade was. And everybody else is just thinking, this kid's the class dunce. And no, I'm like realizing this is the smartest kid in class. The big M stands for moles per liter. We use it a lot. You have to be in molarity unless we're doing KP. All right. So there was nothing about how much HI I started with. That's because you didn't have any. You mixed these two, but there was nothing initially of that. Now, you sometimes will start only with product. Sometimes you will only start with reactant. When you're mixing stuff, that is initial. If it says at equilibrium, that is the E, which I wrote down further. We'll just move our E down here. All right, C stands for change. And this is where the X is going to come in. So you just write ice. Pretty sure you all know how to spell ice. So the change, you always have to move in the direction of the 0. So to reach equilibrium, back to that comment I made, equilibrium means everything is there. You have to have everything there. You cannot have a 0 at equilibrium. So the reaction has to move in the forward direction to reach equilibrium. Now, not every time is the zero on the product side. Sometimes the zero is on the reactant side, in which case you would have to go reverse. But for this problem, since we're moving forward, this is going to decrease by x. This will also decrease by x, and this side will increase by 2x. The reason it's 2x is because of that 2. If that was a 3, that would be 3x. So how much, the number in front of the x is the coefficient. All right, so at equilibrium, this is the I plus the C will give you the E. So you can put a line here if you want. So this is going to be 0.001 minus x, 0.002 minus x, and this will be 0 plus 2x. And that's going to have to equal that number, because we already knew what that number was. But I plus C will equal equilibrium. I plus C equals equilibrium. All right. So, does anybody know what I forgot to do? Oh, I didn't write my K expression. So, your first step is one of two things. And most students, their first step is, I want to do the chart. So do your ice chart. And then before you solve, you do have to write your generic K expression for that equation, products on top, reactants on the bottom. Now, the biggest thing you need to get from this first lecture is that equilibrium is a ratio, products to reactants. It's a balance point. The high majority, like 99.99% of reactions, are two-way reactions. There's very few that are one-way. Now, in our body, you know, there are some, like that phosphate getting attached on the glucose as soon as it enters the cell. It's a one-way reaction. Unless you're in the liver, then everything's two ways, because our liver is magnificent. All right, we're going to solve for K, but to solve for K, we're going to plug in all this information, but we have x's there. So we have to solve for x first. But we know this, that the 0 plus 2x equals 0.00187. So algebraically, you do your magic, get rid of the 0, divide by 2. So you'll find that x is 0.000935. All right, when you solve for x, you can leave units off. I'm okay with x being a number. Your chart needs to have units. Notice my big M. That's important, because if you had done this with the 0.005 and the 0.01, you're going to get the wrong answers. When you plug into K, they need to either be molarity or, what am I going to say? If it's Kp, atms. All right, so now we can plug in. This is my value for on top. And then I plug in, I take this number minus that to find this number. Take this number minus that, find this number, and I plug these in over here, and you will get 50.5. I've done this for 25 years. I know that answer is correct. That answer is dependent on the temperature. So at different temperatures, you might see this question and you'll have a different K. So please realize that. All right, and that's our final answer. We don't have any units. Actually, in this case, you wouldn't. They would all cancel out. But so you would show me what your value is here and here, which you guys can do that in the interest of time. Or get stuck. I am going to be doing live lectures, which I know Aaron and Jim, Ann and Janae will probably come also when they are available. So they'll be here to catch me and stuff. And if we were truly live, we would be pausing. You would all be trying to write furiously as you're texting and stuff. Well, now you can stop while you're texting and then pay attention to me and pause to solve the problem on your own. But I recommend any of you want to come while I'm recording. Absolutely. Wouldn't it be great if we could find a place where I could record where you were like there in the room with me? All right. This virtual matrix, I know you're all there. Let's do the next one. You can always rewind. That is actually a huge advantage of this. So 2SO3 gas and 2SO2 gas plus oxygen gas. All right. That's the equation. It's given to you however it's given. And we look. It says calculate K if blah, blah, blah. So it says SO3 with the little I and then SO3 with the little EQ. So we're going to write our ice chart, and the one with the little I means... All right, another quick comment just from questions over 25 years. I often leave my zero off before the decimal. It's just something, it's an efficiency thing that a lot of scientists and engineers do. I honestly don't care. If you're going into pharmacy, they will mark you wrong if you don't show the zero before the decimal. Make sure the decimal is obvious. You can always use scientific notation. And then EQ, make sure you get the number of zeros right, 0.00244. Please notice in my chart, I have units. So, what's my initial amount for SO2 and O2? It doesn't say there's any. So it must mean they are zero. At equilibrium, you cannot have a zero. But initially, there is a zero, which means we move forward. We always move in the direction of the zero. This side is going to be our negative. This side is going to be our positives. So the direction the arrow is moving is going to be the plus x side. This side is going to decrease not by x, but by 2x. And why 2x? And they all say because of the coefficient. All right, over here, this is going to increase by 2x, and the oxygen is just going to increase by x. So what we know is true is this column, 0.00609. In the chart, I have units. Down here, I can leave off the units, minus 2x. So I plus c equals e. So 0.00609 minus 2x equals 0.00244. You do your algebraic magic, and we get x equals 0.00183. I'm an alchemist, so I get to do that. That's actually the sacred sound for releasing fear from the kidneys. You go when you hit your knees, and it releases it. There you go. Now you're on the secret. All right. This is my equilibrium amount of my SO3. My SO2 will be double my X number. So 0.00, what is that? 366. Capital M. I'm in the chart again. I put a unit, and this one is just X. 0.00183. So, you write your chart. If you have enough information, you finish your chart. And now we can calculate K. And to calculate K, the first thing we do, you must always write your K expression. You will lose points if you don't. Products on top, so SO2 squared times oxygen over the SO3. Again, how the equation is written in the problem given to you, products in this case for the SO2 and the oxygen. And then I plug in these numbers. I'm going to plug it in right now just out of courtesy. I don't know if you can see me, but 0.00366 squared. When you plug into the K, you can leave the units off. In the chart, you have the units. When you solve for X, plugging into K, it had to be molarity unless we did a KP, 0.0. Yeah, so this is interesting. Not only did we have to double the SO2, because it's 2X, we're going to square that. And then the SO3 was given 0.00244, and that one is squared. So I try to put your equation over to the left side, make your chart right underneath it. Some of you are going to have to learn to write in a nice orderly way. And then over on the right side, write your K and fill in underneath, and you plug in and you get a value for K. There we go. We have a value. Hey, let's do something really cool here. Let's talk about that value of K. It is in 2 pages in the notes, but let's talk about it now. The K is the balance point. K is always a positive number, but in this case, my K is less than, my K is less than 0, right? It's below 0. All right, can we rewind? This is why I love having you guys present. See, I'm getting loopy. I haven't had my lunch yet, and it's like 2 o'clock in the afternoon. But it took a while to find this outfit, and it keeps rearranging on me. All right, k is always greater than 0, but it can be greater than or less than 1. It is a ratio. It is always products over reactants. If k is less than 1, it means your denominator is larger. And again, I'm going to go over this in 2 pages. There's a whole page where I go over this, but I want to give you a quick look. That number tells us there's more reactants than there are products. The reactants are dominating this. So this is favoring the reverse direction. So favors the reverse. And that's it. That's what it means. K is less than 1. We have more reactants, so it favors the reverse. So that balance point is not perfect. It has its balance point. As temperature changes, it actually might become 408, and that would favor the products. All right, let's do one more. You ready? So these first 2 examples had us solving for k using the chart. You guys can always rewind and listen. Sometimes your ears, you know, it's one of the things, we have many senses. Supposedly we have 8. So most of us rely so much on our eyesight, but listening. Having this printed out, and you can listen. In the days before YouTube, all they could do was tape me, and then they would listen and jot down, and they did amazing. And now everything's like, whoo, you guys have to see everything, and you're losing. I didn't go for a bike ride yet, so it doesn't matter if you could smell me or not, right? But I smell like flowers. Or patchouli, because that's what's in my hair stuff. All right, this one's a little bit different. Everything's gas, which is great. I'm not going to cross anything out right now. And again, my answers are there as a courtesy to me also. This one gave us a value for k. It says, oh, by the way, k is 280, and it has that little c. It just means we're going to be using molarity. All right. So let's make our chart. I know I had to make a chart because it says what happens at equilibrium. As opposed to that question number 3 at the bottom of the first page, it said at equilibrium, this is what you have. Then you're already there. You don't have to worry about mixing stuff. Here we're mixing. So we start with the IBR. Interesting. So 0.35 moles in 1 liter. So moles per liter, that is molarity. All right. And that's it. That's all it gave us. Well, I know that's initial. And the other ones must be 0. I put a line through my 0 so you don't think it's an oxygen. I had a physics teacher, Wolfgang Snyder. And he always put a line through it. It was the first time I ever saw it. That was like in 9th grade. All right. This has to go reverse to reach equilibrium because everything has to be there. But because the equation was written like this, when we write our k expression, let's go ahead and write it. You guys know how to write it. Just write it. You know, in the old days, I would stand there and say, just write it. Just write it. So you're not just copying off of me and going, what did she do? You know how to do it. One thing you have to get from today, this first hour lecture, is that you know how to write k. You're confident. You guys already wrote it. You went, okay, I have the IBR squared, and you're going, why does she keep using parentheses? Because I won't have a shoulder by the end of all this if I use brackets. But here you can use brackets. It is supposed to be brackets. I know it's going to drive some of you crazy. It would drive my son crazy. All right. My ability to erase the board also. Products over reactants. But we started with the products. Doesn't matter what you start with. It's how the equation's written. This side now is my plus x, my minus 2x. So at equilibrium, this is x, and this is 0.35 minus 2x this is different from the first two on this page. Down here is, we know K. Well, we can do it over there, but I'm comfortable here. So my value for K was 280. It's going to be equal to the IBR squared, so 0.35 minus 2x squared over x times x, the iodine and the bromine. Algebra. Algebra is great. I know I wrote really petite there. I don't know why. All right. So on the next page, I talk about the quadratic equation, but I'm going to get out of it in this one. So about half of you have better math skills than I will ever have. Actually, that's not true. I have really strong math skills because they're up here, because I didn't have to grow up with an Inspire calculator that did everything for me. I used my own brain cells. You could put this into the solve function in your calculator and it will give you two answers. You would need to give me the two answers and then cross out the wrong one. And I'll talk about that more on the next page. All right. Those of you who go, oh, wow, I don't have one of those. Do I need to go and buy a $300 calculator? No. If you do a square root of both sides, so whatever the square root of 280 is, this square disappears on top. So it's now just 0.35 minus 2x. And this was x times x, which is x squared. So that just becomes x. And you rearrange. So as you know how to do this, just solve. Those of you who don't, whatever the square root of 280 is, this number times x will equal 0.35 minus your 2x, right? And you move your 2x over here by adding. And then what this equals, solve for x. And I gave you an answer. So I'm not going to spend the time. If I had this, I was thinking about him the other day. This most wonderful student named David, my very first year. He was in my 100 class, and then he took my 200 class with me. And he was the sweetest gentleman. It was actually when students were older than me, which was like 5 when I started 25 years ago. So, yeah. And so he took me on my first hike of Multnomah Falls, and it was awesome. David was a large man, and so he had this awesome walking stick, and we just walked really slowly. Anyway, I remember doing this for Save 223 in the summer, and his algebra skills weren't the best, and so we walked through them slowly, or he would stay for office hours. Office hours is the time, if you need help with the algebra skills, he got an A. He got an A in every class because he wasn't afraid to come to office hours and say, I need help with the algebra. I need specific what you need help with, and we can walk through it. All right. So, right, we had to finish the chart and then plug in. Different from the first two questions, where from the chart we could solve for x and then solve for k. This one, we have to use k to solve for x. And so I gave you the value. You guys can see the answers there. You solve for x equals 0.019. And then you go back up here and you find all your numbers. So those would be 0.019 and this would be 0.35 minus double that. Now those of you who did the solve function, you got two values. Your other x is impossible because I didn't write down what it was. It was either a negative number. X cannot be negative. The change can be negative, but x itself cannot be negative. Or x was too big. And so when you would do this, you would get a negative. That's the best I can explain it without you being present and me seeing your work. And that's with the office hours. And those of you, you should all, this is not the first class you've done in this crazy new format that the world has decided has bestowed. We can share screens. You just have to remind me, I have an overhead projector onto a whiteboard and I can work it out on that. I just keep forgetting I have that because, right, I'm retraining also. All right, let's keep going. Yeah. All right. We can do one more page here. You can, of course, stop me at any time. Go take a break. I'm going to keep going. And we're going to put that light on again. I don't know if that helps or not. All right. I wanted to show you one with a quadratic. Those of you who have the solve function will be able to fast forward probably through this. We plug in our pieces. We have 1 mole per liter of the hydrogen. So 1 mole per liter. And this one we have 2 moles per liter. And there's nothing in the HI, so that's my 0. So we're going to move forward. So my change, these are my minus x. This is my plus 2x. I gave you a value for K, 50.5. So at equilibrium, this is going to be 1 minus x. This is going to be 2 minus x. And this is going to be 2x. So we're going to have to plug into our K expression. So K equals HI squared. Again, try this. Set up your K and then start me again. I'm going to keep going. Hydrogen times the iodine. HI is squared. Biggest mistake students make is this step. They rush and they forget to show the squared. All right. So now we're going to plug in. The K is 50.5. The HI is 2x squared. The hydrogen is 1 minus x, 2 minus x. You cannot square root your way out of this one to get rid of the square. You have to rearrange, right? You distribute this part out. So you get what? 2 minus 3x plus x squared. That's this bit here. Here you have to square the 2 and the x, so you have 4x squared. You got to move this whole piece here to this side, distribute it out with the 50.5. You got to move everything to the same side. And so once you do that, you would get 46.5 x squared minus 151.5x plus 101. This is just me reminding you, you're going to see, I believe during the term 1, maybe 2 quadratics. They are on take-home stuff. Those of you who have a calculator, you would state solved with TI-89. In which case, you're not going to have that line. And you're going to say my x is equal to, this one I actually have, 0.935 and, or 2.323. So you would have your initial setup. You would say solved with the TI-89 or with inspiration, right? And then you give me 2 values. We're not done yet because we have to pick one. Those of you who don't have one, don't buy it. 2 problems, you can work it out. And those of you who are really geeky, I have some students who are in graduate school now for math. They worked it out longhand. They had a TI Inspire, and they're like, it's just so fun doing the quadratic longhand. And that's what I did. So this is your A value. This is your B value. This is your C value. Now, for some of you, you're hyperventilating, going, oh my God, the quadratic. Can I drop the class? Well, you could. But like I said, I avoid it. I didn't say this yet. You're going to see it twice. There is one question on the homework. And I actually, either on the homework or the worksheet, that says this is a quadratic. So you will figure it out. You can do it, work it out on a piece of paper to get to this point. Then you plug in and you give me your 2 x's. And you can say, work on extra piece of paper. That's at the end of everything. Yeah. Now, no matter what, you get 2 numbers. I avoid these on test because it is so freaking unfair for those of you who have the solve. However, the people who miss this the most are the people with the TI-89s. Because they don't know how to put it, their fingers. We have little fat fingers and little keys. And so the people who do it longhand always get it right because I avoid them on test. It will be like the other questions. I just wanted to show you one because it is reality. It can happen. All right. it cannot be, if you have two positive numbers, it can't be the larger one. Because here, 2 minus x, if you had 2 minus 2.323, you would get a negative. So you would show me your two answers, and then you can cross out the one that's not possible. This is what we would have, so we can go up here and plug in. And if you want, you would just give me then 1 minus the 0.935, which would be, what, 0.065. Now you need a unit, molarity. And then, right, I gave you your answers. This would be 2 minus that, so it would be 1.065 or 1.07. And yeah, this should have 3 sig figs. I think it must have been a 0, would be my guess. And then there we just double 0.935 and we get 1.87. The biggest key this term for all of you is being able to show your work, because you are going to have to show your work in a way that anyone could follow it. If I'm spending 10 minutes trying to grade a question, even if you get the answer right, if I cannot follow it. So you have your ice chart and your work, you can do it over there or over here, depending on where you have the most space, and you can number the steps. All right, that's our quagmire. Let's do these last two problems. The good news is these two, and then your teacher has to take a break, which you won't know. Other than the video will stop. These last two problems are Q problems. Not for quadratic, but because Q is such an awesome letter. Q stands for reaction quotient. Reaction quotient. I gotta spell it right, sorry. All right, it is a comparison to K, so let me solve the problem, the example, show you how you can recognize that it's a Q problem and celebrate and say, oh, I love Q. Because there's this really cool trick a student showed me many, many years ago. So we have our equation, nitrogen plus 3 hydrogens. This is why you want to print the notes so you don't have to do all this writing that I'm doing. In 2 directions uphill, right? All right, and it gives you a K. 0.105. All right. So we write our K expression. Oh, we can do our chart and write our K expression. So ICE, we're going to find out we don't need a chart. So it tells me I have hydrogen, 2.00 moles. It tells me I have nitrogen, 1.00, it's my I, moles. Why we have units, so we know this was moles and not molarity yet. And over here I have 2.00 moles. Oh, it's all in 1 liter, so I can just say per liter or change it to molarity, which is great. Oh, this is different. There's no 0. We mixed everything. We're not at equilibrium because the question doesn't start by saying at equilibrium you have this, this, this. It's saying you mix this, what happens? That is a Q problem. When everything is present initially, it is a Q problem. So pause me and write that down. Everything, you have an initial, there is no 0 in the initial, it's a Q problem. Hey, you stopped me? Now we're back. So Q, we write the same as K, products over reactants. NH3 squared, because of the 2, over reactants. Nitrogen times the hydrogen. Hydrogen we have to cube. All right. The difference between K and Q. K is E, equilibrium values. Q is initial values. It's going to tell us where we start, and then we figure out what we have to do to get to that balance point. So we plug in our numbers. So 2 squared, notice the chart has units, but when I plug in, you can leave it out. 2 squared over 1 times 2 cubed. Don't use your calculator, do this by hand. 2 squared is 4. 2 cubed is 8 times 1 is still 8. 4 over 8 is 1/2 or 0.5. We have 3 sig figs, sure. That is not K, that is Q. So now, this is cool. This is a trick a student showed me. And maybe it's online now. This is a student like 20 years ago before YouTube. And none of the books show it this way. They show it the other way, which actually I taught, and this is much easier. Do you guys know the alphabet? Let's sing it. A, B, C, D. Which comes first? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. All right, put them in alphabetical order. K comes before Q in the alphabet. If you ever forget, sing the alphabet song while you're washing your hands. We've all become really good at it. All right, the alligator eats the bigger one. So K was 0.105 and Q was 0.500. Q wins. Q is larger. So this is alligator. So I homeschooled Joey, and I also taught English as a second language to many people. The alligator eats the larger one, so his mouth is eating the larger one. This is what's really cool. His nose points what direction it goes. His nose is pointing that way. What's that mean? She went on a tangent. No. The reaction moves. Can you see that? Yes. Oh no, I went over a minute over an hour. Reaction moves reverse to reach equilibrium. Got it? If it had moved forward, we'd move forward. So it's not saying it favors the reverse, it's saying the reaction moves reverse. What do you have to write down when I say, can you explain your answer? Because I'm going to ask you to explain. It's what I did in my little answer there in parentheses and italics. Q equals 0.500, again, no unit. So K is less than Q, which means the reaction proceeds in the reverse. Oh, so we have to finish answering. So will more NH3 form? It's moving reverse, which means NH3 is going to react more. So you're going to end up with less NH3. You can use words, or you can just say decrease the NH3 at equilibrium. Not to 0, but less than we started with. All right, let's do the last one on the page. Well, I'm erasing. Why don't you guys try it? Well, I'm writing it out. Or you like watching the square? So much nicer when I had a limit. When I'm videotaping, I can go on forever. I can go on as many tangents as I want. All right, I keep seeing the same problems here. I don't know why. I was not being creative. I do get creative eventually, for those of you who know me. By the way, Devin, welcome back. So I'm hoping your name's still on there when we start. Welcome back, all of you. Megan, Jessica, Brian, assuming you'll all be here. And all of you new people, hopefully I get to meet you. That comes my office hours. All right, and we're going to make a chart. So initially you might write ICE. There is another way you know it's a Q problem. It will say, is the system at equilibrium? Or what happens to reach equilibrium? That's also a clue that tells you it's a Q, is how these questions are worded. But everything's present initially. So my HI, 0.020, put a unit. It is moles. Hydrogen, 0.010 moles. And the iodine is 0.010 moles. So on Show Your Work, you need to show me where the numbers are coming from. And then that's over 2 liters. They're all mixed. Everything's together. It's a closed system. This is a Q problem. So we state our Q expression in Show Your Work. If you don't write out your Q expression, you're not going to get full points. It is the same as your K expression. Remember, you can stop me at any point. Fill in, solve. Right, so this is 0.01 squared. This is 0.005. 0.005. We punched it in. And I get Q equals 4. So now we compare to K. K was given in the problem that K is 50.5. Alphabet, K always comes before Q. K is 50.5. Oh, you can't tell me I'm going too fast because you can stop me. Do it yourself. K is the larger number this time, so the alligator eats the K. His nose is pointing towards Q. So, proceeds forward. So, is the system in equilibrium? No. Unless K and Q are equal, so the reaction moves forward. So you can say reaction moves or proceeds. It's to reach equilibrium. Or you can just show the arrow. You can just do K, Q, put an arrow. I'm writing words because a small percentage of you, which is probably just one of you, likes the words. And you probably went to school with nuns and they slapped your wrist or something. If you didn't write a full sentence, is that a grammatically correct sentence? All right. So, reminder, I probably told you that. I found my periodic table. It has all the elements. It's so cool. And it has famous people down here. So Enrique Fermi was picked. I don't know if Mendeleev has by the time I post this, which will be in a month. All right. It's been awesome. I will see you soon. To do the other pages, I'm going to go ride my bike and take a break. And then we'll finish this. Blessings.